We present Laser, an efficient and accurate 2D visual localization framework. In this work, we are interested in localizing images on a floor map. And here is an example of our result. Our method estimates the likelihood of every location on the map, and the final estimations are extracted from the maximums. The very recent works adopt machine learning into Monte Carlo localization to solve the problem. Their key benefit is the seamless support for color images and the learnable uncertainty modeling. However, their heavy two-stage process for every single sample that requires rendering and encoding limited their sampling rate to only about 20 Hz. This further limited their usage in applications that require real-time tracking. In this work, we greatly improved the sampling rate to over 10,000 Hz and reduced the rotation dimension from the sampling space. This allows us to densely sample a house-level map within no longer than 1 second, while existing methods may need a few minutes. And at the same time, our work largely outperforms existing methods in accuracy as well. The secret behind the 10,000 Hz is our proposed latent space rendering that can directly render a feature vector without extra encoding. The idea is very simple. Consider a floor map under 2D point cloud format. We process it with the point net to get the per-point feature embeddings, and the latent space rendering simply aggregates features from the visible points onto a circular structured feature. And the design of this circular feature eliminates the need for drawing samples from the rotation dimension, since we can simply rotate the circular feature instead. And we grid sample the map to create circular features everywhere. However, naively doing this does not provide a satisfying result, since such feature aggregation disregards important geometric information such as the viewing ray length. And the idea for fixing is also very simple. So instead of assigning a single feature per point, we let the point net infer a feature lookup table, which we call the codebook. And at the rendering time, the feature of each point is determined from the codebook indexed by the viewing ray geometries. And here we consider the incident angle and the ray length, so we have two codebooks. And the final feature embedding will be the sum of these features. With the codebook scheme, the point features are dynamically determined at rendering time, encoding fine-grained view-dependent geometries, resulting in very nice and accurate result. For the images, we process them into circular features according to the geometric correspondence between their feature map and the circular feature. So for panoramas, we simply squeeze the vertical dimension of their feature map to obtain the circular feature. And similarly, for perspective photos, they will have a partially masked circular feature. Next, with the image and the map circular features, we can estimate their relative rotation simply by a uniform sampling and keep the best. And we do this for every pair of circular features, so all map circular features will be rotated to align the image circular feature. And finally, we can obtain a likelihood map by measuring their distance. We apply non-maximum suppression on the likelihood map to extract the candidates. And the training is still very simple. It's just the triplet loss. We use the image circular feature as the anchor, and positives, negatives are sampled from the map. And here's the result with the panorama queries. The baseline MCL uses the ground truth stats as input and has same number of samples as ours. And here's an example showing the results with changing the image of FOV. So basically, the wider FOV we have, the better result we have. So for the panoramas, our method achieves an overall accuracy at about 5 cm with 97% recall on the synced dataset. For perspective photos of limited FOVs, the semantics plays an important role, and our method has significantly less ambiguities. Here we show results when different content is observed. Basically, the corners or semantics are more favorable than blank wall in solving the ambiguities. With perspective queries, our method has an overall 57% recall and a 20 cm accuracy. We also visualize the codebook and the map metric space using PCA and TSIN. And finally, we show the codebook encoding scheme provides strong interpretability that we can inverse match the image circular feature to the codebooks to recover its semantic labels and the layout. And in this way, we can clearly see what's going wrong. And I want to thank you for watching and welcome to Scan Code for more details.